Let's begin with the idea that waves reflect at a boundary. Here our string is tied to a post. We call that a boundary anytime the path of the wave encounters something different. So this is the boundary, and watch how the wave reflects. Now let's look at this with a simulator. Here I will send a pulse down the wave, or down the medium, in this case a string. And you see at a fixed boundary, this is called a fixed boundary, the wave reflects and it changes phase by 180 degrees. It goes from being a peak or a crest to a trough. And it happens at both ends. Both ends are fixed boundaries. And you'll notice here the damping is none. So in real life, waves die out on a string. We call that damping. Friction with the air, resistance to motion in the string, all sorts of things contribute to damping. And we see there that the wave eventually dies out. Now we can change this to a loose end. Now this is free to move. And when we send the pulse, now we see the wave is still reflected, but now the phase does not change. You see over here at the fixed end, the phase changes. At the open end, the phase does not change. But a very important idea is it still reflects. Now, what happens if we continue to stimulate this end? We'll oscillate it with a continuous periodic waveform. Now the waves will reflect, but I'll have two waves traveling, one to the left and one to the right. And of course, we know that when waves are in the same place at the same time, they interfere with each other. Now, I've placed our ruler here so that we can see the amplitude of our wave, and notice when they reflect, they start to interfere, and we get some constructive interference, you notice. The amplitude of the wave is higher than it was originally, but if we wait a while, this is not a perfect standing wave. The frequency is not exact so that the wave remains. We get now some destructive interference. Look at that, and back to constructive interference. So it varies. Sometimes it's constructive, sometimes it's destructive. During the time of maximum constructive interference, we say that it is resonating.
Another way to look at resonance is to look at what are called modes of vibration on a string. A mode is just a frequency at which a string, like the one shown here, wants to vibrate naturally, in exactly the same way as a simple harmonic oscillator wants to vibrate naturally at some frequency. What we have here is a string that's anchored on one end. On the right hand side, you can see it's tied onto a clamp that's clamped to the table. And on the other end, I've attached it to what used to be a perfectly good mid-range driver and now won't work very well ever again. So here we can see what's happening. I'm driving the loudspeaker with an amplifier attached to an oscillator. The volume of the amplifier determines the amplitude, so how much the woofer is moving up and down. And the oscillator I then use to determine the frequency, which is how many times per second it moves up and down. And as you saw a minute ago, the other side of the spring is attached to a clamp. I can change the frequency. This is about 5 hertz going up to, this is something like 10 hertz, 9 hertz or so. So 9 times per second going up and down. Or I could go the other way. I can go back down to 5 hertz. That's 5 hertz right there. Or I can go all the way down, for example, to 1 hertz. So this is moving up and down and back up again 1 time per second. So this is the whole system again. I'm now driving it at something like 5 hertz, 5 times per second, and I'm going to increase the frequency bit by bit. This is maybe 6, 7 hertz, up to 8, 9 hertz. And suddenly you'll see when we hit 11 hertz, which I've already found out to be a magic number, what will happen is that the string will suddenly behave differently. This is 10 hertz, and this is 11 hertz right here. So you can see now, we'll freeze this. The string is in what's called its first mode of vibration. This is the frequency, 11 hertz, for this particular string and this particular setup. This is the frequency it wants to resonate at, the lowest one, this 11 hertz, so 11 times per second. What you can see is that even though we haven't changed the amplitude the amount that the driver, the woofer, is moving up and down, the amount that the string is moving up and down in the middle has changed dramatically. And that's because it wants to ring at this frequency. Let's start the video again and see what happens if we increase the frequency again. So this is 11 hertz. Let's move it up. This is going up to something like 15 or 16 hertz, right? Let's see, right here. So we've changed now, we're moving faster, still at the same amplitude on the woofer. Now let's go to 22 hertz and see what happens. At 22 hertz, and remember our first mode of vibration was 11 hertz. At 22 hertz, you can see what we have here is the second mode of vibration. So this is the next frequency up that the string wants to vibrate at. 22 hertz is 2 times 11 hertz, so it's twice the frequency of the first mode of vibration. You can see again, I've frozen the video here so you can see what's going on. What's happening now is that the string naturally stops vibrating in the middle, but we still have two large excursions, 2 points where it's moving much more than the woofer is, on either side of that point where it's stopped. But this happens naturally. I haven't done anything to the string to make this happen other than to put in the frequency where this mode wants to vibrate. So let's start the string moving again. I'll start the video moving again, and we can see what happens if we keep going up in frequency. So this is still 22 hertz, and then we change to something like 25, 26 hertz, and we lose that resonance. Now let's go to 33 hertz, which will be the third mode of vibration. Here we are. Again, I've stopped the video so that you can see what's going on here. It's basically the same thing again. We have a frequency coming into the system, still at the same amplitude, but now the string naturally wants to resonate at this frequency, but in order to do that, a smaller section of the string has to be vibrating. So it naturally stops vibrating in those two sections you can see there in the middle. And we have these three areas where the string is vibrating up and down more than the amplitude that we're putting in from the woofer. Let's start the video again and go higher in frequency. This is 33 hertz. Let's go up to 37, 38 hertz and up to 44 hertz. Right there. So at 44 hertz, we have the same behavior again. Now we have 3 points on the string where it's not vibrating and 4 points where it's vibrating more than the amount of energy that we're putting in, or the excursion that we're putting in using the woofer. So this will keep happening as I go up in frequency. This is 44 hertz. If I multiply the original by 5, I get 55 hertz. And of course you can see it's the same behavior as I keep going up and up and up. And if we then change the frequency back down to say 33 hertz, this mode goes away and it automatically settles into its third mode of vibration. So the thing to remember is that the string wants to do this. So if we had hit it with an impulse, if we had plucked it like a guitar string, all of these modes would be singing together at the same time. And that's what gives a guitar string the characteristic sound that it has. It's the combination of all those frequencies playing together simultaneously at different amplitudes that makes the sound of a guitar or a violin or a harp or a piano. That's what the balance or the relationship between the amplitudes of those different harmonics playing together at the same time is what makes those instruments have their characteristic sound.
Okay, what I've got here is an app on my iPad called FFT Plot, and it allows me to see all the frequencies present at once. So here's the frequencies present in my voice, and just to demonstrate, I'll use some tuning forks. This one is 2000 hertz. There you can see the spike at 2000 hertz, 1000 hertz, This will allow me to look at the frequency content of different instruments and see what their timbre looks like. Notice here the lower guitar strings on the right vibrate more slowly than the higher pitched guitar strings on the left.
The vibration one observes in a guitar string, once it has been plucked, is the sum of an infinity of stationary waves called harmonics, or modes of vibration. The tension, adjusted by the turning pegs, and the length of the string impose upon the waves that are propagated certain conditions of frequency and wavelength. The two extremities of the string define limiting conditions, which impose zero displacement at these points at all times. This simulation enables us to observe the first four harmonics separately, which is not possible in reality. The stationary wave that has the greatest wavelength and is in accord with the limiting conditions is the first harmonic. It is also called the fundamental. It has two nodes of vibration at the two extremities and a single antinode in the middle, which gives it this very characteristic bulging envelope shape. Its resonant frequency, noted as F0, depends on the length of the string. The shorter the string, the higher the frequency is, and the higher the pitch of the sound is. A harmonic of rank n is a stationary wave with a frequency n times the frequency of the fundamental. However, even if the series of harmonics is infinite, their respective amplitudes decrease very rapidly, and only the first harmonics, among which is the fundamental, are perceived by our ears.
Why that an A note on a piano sounds different than an A note on a guitar, even though they're both playing an A note. This got to do with the harmonic content. The harmonic content of a sound can be categorized in two groups, and that is the fundamental frequency, which is the sine wave which determines the pitch of the sound, and then we have the harmonics, which are the sine waves that are whole multiple numbers of the fundamental frequency. The fundamental frequency of an A2 note is 110 Hz. The harmonics would then be at 220, which is the second harmonic and exactly an octave up. Then we've got 330, which happens to be an A4 note, that is the third harmonic. The fourth harmonic is again an octave higher. So you can see that a doubling in frequency represents an octave. The 7th is an unrelated pitch, and the 11th again is an unrelated pitch. And that simply means that our ears really can't relate a pitch to it. Let's take a listen at the harmonic scale of this A2 note. So in this project, I'm going to take a look at the fundamental frequency, and I'm going to take a look at the instrument sound, and I'm going to compare that with a frequency analyzer so you can see the harmonics.
So guitar strings are fixed at both ends, so they are constrained to having nodes at both ends. And here is the harmonic series that we saw demonstrated just a minute ago. But it's also possible to have a bar that is free to oscillate at the ends, or a piece of metal. This is like in a glockenspiel. It vibrates back and forth, and the nodes you see are not at the ends. The ends are free to vibrate. So we can show you this in a animation here. Here is an exaggerated vibration of the glockenspiel. Right here is the node, and right here is the node, and we can physically touch the vibrating bar at the nodes, and it will not dampen the oscillation. Check it out.
Now, these are just normal you can touch it. These are just normal aluminum rods, and they've been scribed. I don't know if you can see these black little lines there. And the first one we're going to do is the T rod. Remember the flexing tuning fork? And flexural or bending waves, they like to just stick around. Look at that. Again, no batteries. Just keeps going. Now, you'll notice that I'm supporting it where this mode, this standing wave, has no motion, right? What if I change that? I just kill the mode. Here's another rod. And this is the L rod for longitudinal. And I can excite longitudinal motion here. You put that there? No. Can you hear it? Okay, any bowed musical instrument players, any baseball pitchers? What do you do to...
allowed?
What do you do?
Baseball.
Is that allowed?
Yeah.
Oh, yeah. What do we need here? One word starts with R, and it's not resonance. Not resonance. Yes. Okay.
It's right there.
Oh. Okay. Let's see if we can hear it this time. Where's the sound coming from? Where? Only the ends. Only the ends. Amazing.
Okay. We're going to show you that vibrating things put out lots of different frequencies. My voice, you can see, has lots of different frequencies. The tuning fork is a very specific frequency, but this metal pipe, I'm going to strike it with a hammer. And you can see the many different frequencies that were showing up. Let's try it again. Okay, so this pipe is free to vibrate, and it has many different wavelengths, many different frequencies. Remember, frequency and wavelength go together. So if I see multiple frequencies, that means I have multiple wavelengths. This pipe is vibrating, and you saw with the string that I demonstrated in class, there's nodes and the antinodes. I'm able to touch the pipe at a node so it can vibrate here, but at the node it's not vibrating. So if I will block all the frequencies that don't have a node right here at this spot. Looks like a little under 500 hertz. Now I'm going to move my finger to a different location on the pipe, and now only frequencies that have a node at this location will be heard. Let's try a different spot right here. So I'll play the E and then the GBE without any frets held down. Now I'll just slightly touch the string. So the professor that had the aluminum rods, he was able to run his hand down the rod with rosin on his fingers and cause it to vibrate longitudinally. We can have tubes like clarinets and things like flutes, instruments like that, where the vibrating medium is air, and it is possible there are some tubes that are open at both ends, and there are some tubes that are closed at one end. So let's look at the open at both ends first. Here we see the fundamental frequencies of a standing wave in a tube that is open at both ends. Because it's open at each end, the air is free to move, and this is the way we normally draw it, because this is the easy way to draw it, the displacement of the particles. Here you can see at the node, the air molecules are not going anywhere. They're staying still. But at the antinodes, where there's maximum displacement at either end. And we'll show you some examples of some musical instruments that are open-ended at both ends. And then we'll also show you some that are closed at one end. Here you can see at the closed end, that prevents the air from vibrating. So that's where my node is. But again, the open end is an antinode. This is open at both ends. This too is open at both ends. Straw, cup of water.